Welcome, everybody, to this Thursday VTSS. And it's my pleasure to have here Tommaso Proietti from Tor Vergata as the speaker and Liudas Giraitis from Queen Mary as our kind guest panelists. Tommaso is talking about separating long memory from short. And then, Tommaso, the floor is yours. Thank you very much.
Thank you very much, Alessandra, and thank you to the organizers of this nice seminar series. Hope you can see my slides.
Yes, we can.
Okay, good, good.
Thank you.
So I'll be presenting a joint work with Alessandra herself, Shelton Piris from the University of Sydney, and Sanjaya Dissanayake from the University of Macquarie, Australia, always. So what is this paper trying to do is isolating and quantifying the role of the short memory component within a persistent time series, possibly not stationary, as we will see. And the motivating papers are listed here. Essentially, we looked at inflation series and realized volatility time series. With respect to inflation, so the time series that we analyzed is the monthly inflation rate for the US, which is plotted here, along with the sample autocorrelation function. And we will consider this time series as possibly displaying persistent long memory. And we will try to separate what is persistent from what is not persistent. So we will try to distill the short memory component in a couple of ways, as we will see. Inflation could be relevant. There is a nice paper in the Journal of Time Series Analysis by Uwe Hasles and co-authors that show that fractionally integrated models can outperform short memory models such as ARMA or ARIMA, even ARIMA models for this class of time series dealing with inflation. And there is also a substantial literature dealing with the separation of components of volatility. For instance, Engel and Lee have a very popular paper, and Amado and Terasvirta, they consider time series of asset returns and try to distill the long-term volatility from the short-term volatility. And then there is an important literature on realized volatility time series. The time series perspective for a long time has been that this time series can be characterized as very persistent time series with characterized by possibly non-stationary long memory. To this view, there is a different characterization according to which the quasi-difference realized volatility time series could be characterized as anti-persistent. This is the rough volatility literature, which has quite a lot of importance in financial mathematics. Now, there is a nice paper by Lee et al. That show that actually these two views are not in contradiction, and they may be a reflection of observational equivalence of these two. But the topic of roughness in volatility is something that we address in the paper as well. This is the daily realized variance series for the Standard & Poor 500 index. This is the plot of the time series in logarithms, in a logarithmic scale. And as you may see from the sample autocorrelation function, the sample autocorrelations decline very slowly with the lag. So this is the basic motivation for the for the paper. And how do we contribute? Well, we propose two ways of distilling the short memory component from the long memory one. And the first one is based on a decomposition of the input response function, essentially based on the Fourier representation of the logarithm of the spectral density. So the motivation comes from there. And we show that the input response function that can be derived from it can be decomposed additively into a long-term component and a short-term component. Another decomposition that we consider is mostly in the tradition of the Beveridge-Nelson kind of decomposition. as we will see. Again, we decompose the time series into a fractional noise component and a short memory component, which is typically anti-persistent for the class of processes that we consider. We apply this to the compositions to time series of inflation in the US and realized volatility for the Standard & Poor 500 index. And we see that the permanent component is very jagged and irregular, which motivates the introduction of a measure of roughness for discrete time series. This is what we eventually propose to characterize the roughness of these sample paths. Okay, so the setting is the following. We basically consider a class of fractionally integrated processes, such as this, displaying possibly long memory. And so the ingredients would be the following. B would be the backshift operator, and 1 minus b to the power d is the fractional differencing operator. D is the memory parameter. What is the process that we consider? Mu would be the reference level of the time series. It would be the unconditional mean. And the epsilon t is a short memory process. So the process will display stationary long memory if d is less than 1/2, as we know. And it is anti-persistent if d is negative. So that's when d is below 0. And we also consider non-stationary long memory, which arises when d is between 1/2 and 1. So we also consider this possibility. And we will assume that the process has started in the indefinite past. So the reference class of process is the type 1 fractionally integrated processes of order D. So this is what we consider. Now, the two models can account for this type of long memory, and they arise when epsilon t is modeled as an ARMA process, stationary and invertible. This is one possibility, in which case we consider the class of Arfima processes. And secondly, we consider the case when epsilon t is an exponential model for the spectral density, right? So this originates the class of fractionally exponential processes that we also consider here. So to be more specific, this is what we assume. So this is the basic setup that we consider. We consider this class of fractionally integrated processes of order D. D will be the memory parameter. As I said, it will be in the range from 0 to 1. So we consider possible non-stationarity. And epsilon t is a stationary linear process with this representation. Zeta b will be the Wald polynomial of this process. And the coefficients of the lag polynomial will satisfy these two conditions. First of all, they are such that the spectral density of the process is bounded from below and from above, so it's non-zero, it's strictly positive and bounded from above, as implied more precisely by the second assumption. The second assumption is an assumption about the summability of the coefficient of the Wald polynomial of the short memory components. And for a given S, which is greater than 2 minus D, D is the memory parameter, then the absolute value of this coefficient times 1 plus j to the power S is a summable sequence. So we assume that the sequence, the series is finite. Finally, Xit, which are the shocks to the short memory process, are a martingale difference sequence. And they will have also a constant conditional variance. So we assume this for the Xit. So that's the main assumption that we make about the generating process. And given these assumptions, the possibly pseudo spectral density of the process can be factorized into two components. The first component is the square gain or the fractional differencing filter, this filter here. And f epsilon of omega is the spectral density of the short memory process. Now, given that given the assumptions about the short memory process, the logarithm of its spectral density is a periodic function, and it's bounded also. Its logarithm can be expressed as infinite Fourier series as a trigonometric polynomial. And the coefficient ck of this trigonometric polynomial will be referred to as the Capstral coefficients, and the sequence of the ck's will be referred to as the capstrum of the short memory process, right? So that putting the things together, the logarithm of the spectral density of the YT process can be expressed like this, right? So it's a function of these cosine terms, and this is the logarithms of the square gain of the fractionally differencing filter. So referring to this expression, now we can also consider the Fourier series expansion of this term, substituted into the formula 5, which is this one, right? And we get this nice representation for the capstrum of YT. So the capstrum of YT is a sequence of a CK star coefficient that has this nice form, right? And the long memory contribution, you see already that there is an additive decomposition of the capstral coefficient of YT. And the long memory will contribute by this hyperbolic sequence where D is divided by K. And CK are the capstral coefficients of the short memory component. There is also this nice interpretation for C0. C0 is the logarithm of the one step ahead prediction error variance. So it's the logarithm of the conditional variance of YT given the past. Okay, so this is the starting point. The motivating observation here is that the capstrum decomposes additively into the short memory contribution, CK, and the long memory contribution, D over K, right? Now, we can characterize further the CK in the case when the short memory component is an ARMA process. If the short memory process is an ARMA process, then the CK coefficient, the capstral coefficient for the short memory have a nice form. I will not bother you with the technicalities, but essentially the capstrum of the short memory depends on the inverse of the roots of the autoregressive polynomial, the AI, and the inverse of the roots of the moving average polynomial, the BI, according to this formula. But perhaps it is best if we illustrate this with a particular case, which is the Arfima 1D0 process, which is this process here. Phi is the autoregressive polynomial, which is less than 1 in modulus, and the root of this polynomial, of the autoregressive polynomial, is A, which is the reciprocal of phi. So given that result about the capstrum of the ARMA process, then the capstrum of the short memory component, which is the AR1 process, it's phi to the power k divided by phi k. It takes this form. And we have this nice form for the capstrum of YT, which is now, it's a constant D, the memory parameter, divided by K, and the additive component due to the short memories, this geometric sequence modulated by an hyperbolic sequence. So phi to the power K divided by K. Similarly, if you have an Arfima 0D1 process, then the capstrum becomes of YT is again the sum of two components, D over K for the long memory minus theta to the power K divided by K for the moving average component. Notice that the moving average representation here has a minus sign. Okay, so what is the next step? The next step, we provide a decomposition of the coefficient of the infinite moving average representation of the process, and also of the infinite autoregressive representation of the process. So let us consider first the infinite moving average representation of the process, which is this, right? So the coefficient of the infinite moving average polynomial here, which is given here, are due to a result that is well known. It's not our result. It's due to Puramadi and Hurwicz. It has been derived several times in the literature. And this result that we exploit is that the psi-j can be constructed from the Kepstral coefficients of the YT process using this recursion. So you have a recursive formula for getting the psi-j coefficient of the moving average representation of the process from the CK star. Okay. And we use this result since the CK star have an additive decomposition, there will be an additive decomposition of the psi-j. So this is our next result. Similarly, for the infinite autoregressive representation of the process, we get this result, which is again due to Puramadi and Hurwicz. You can get this coefficient from a recursion that involves the Kepstral coefficients of the YT process, right? And this is the recursion. So we exploit these two recursions to provide the following results. And now the result is the following. Let us consider the coefficient of the infinite moving average polynomial. This coefficient admits an additive decomposition. And the additive decomposition is made up of two components, the long term or long memory coefficients and the short memory ones. So L will stand for long and S stands for short. Now, this additive decomposition is such that the psi-L, the long-term coefficients, are obtained via this formula. Essentially, what it does is the following. You sum the first j coefficient from the zeroth coefficient to the j minus 1, you average them, and then you multiply by d. So that's the formula. And the residual ones are the short-term coefficients. And you can show that the psi-L coefficient go to 0 as fast as the original psi-j coefficient go to 0. So they have the same rate of convergence to 0 as the original psi-j coefficient, as the original long memory coefficients. Whereas the psi-s go to 0 according to a rate which is j to the power d minus 2. So if this is in the range from 0 to 1, this psi-j coefficient will go to 0 as an anti-persistent component will go to 0, right? So that's the logic of that.
Tommaso,
Okay. Yes,
can I ask
please,
you?
Liudas.
Okay, now we have this decomposition, very beautiful results. This slowly decaying part and short, and this short memory part, phi sj. Now, when we have short memory, you expect exponential decay of the weights, like link in arm, AR, and here you get the bound j d minus 2. Is this exact bound, or maybe you mean just upper bound? You know, what would we have there in case of ARMA models?
So in case of ARMA models, you get it's an upper bound, yes. So you could go faster than that, right?
Good fast.
You can go faster. So this is just based on the assumption here. So assuming this.
Okay.
So for processes that go like this, of course, when you have an ARMA process or a fractional exponential process, they will go faster to 0, right? So that's, I would say, an upper bound in this sense.
Yeah, good.
Okay, so that's so essentially here, given the range of d that we consider, they will go to 0 like this. So this is what we can prove with that assumption. But yeah, in other settings, more when you have a parametric model for this, they can go faster to 0. So this will be satisfied anyway. Okay, so that's the decomposition into these two components. And the same can be done for the pi-j. For the pi-j, you get a decomposition due to the additive decomposition of the Kepstral coefficient. Then you would have the long-term or the long memory component and the short memory component with a similar result. You see now that's the pi L would have a minus in front, but the story would be about the same. And you see, as far as the rate at which they go to zero, then for the long-term component, they would be going to zero at the same rate as the original pi j coefficients, and the psi s will go to zero faster according to this rate.
Well, one more
Yes,
question.
yes, Liudas.
Tommaso,
Yes,
in
please.
in assumption one, you assume that d is less than one. So it covers two cases,
Yes,
stationary and non-stationary. Now,
yes.
when d is greater than one, half and between half and one, then your psi Lj, they may decay to zero very slowly. It's just they decay to zero. And my question was, how should we understand then those series? Because we got some series, and in which sense do they converge then? How should they interpret? This is very clear in the case when we have stationary process, Alfima process, we get this decomposition fine. But assume that now d is between half and one. So what happens then? Here.
Yes, so they will behave. I will provide case studies in the examples where actually D is in this range between 1/2 and 1. And what you get is essentially an anti-persistent component. That's what you end up with. So this pi coefficient go to zero quite rapidly, as we will see. Just to illustrate, just previewing some results, this is the psi sj for the inflation time series. So you will get, when you estimate the model, the psi j would behave like this. This is the psi j obtained. Here I estimate a fractional exponential model, and the long memory parameter is slightly above 1. It's actually, you see, I estimate 0.54. So it's slightly above 0.5. So that's the pattern of the psi j. The long memory component will be this. This is the behavior, and this is how the psi sj go to zero. The pi sj go to zero like this. So they are zero quite rapidly here. So that illustrates a case where, we are very close to the 0.5, but later on I will also deal with with realized volatility in which you get something slightly above 0.5, even more.
Tommaso, can I just follow up on?
Yes, Majid, please.
Sorry, it's just such a delicious result. So if the criterion is I want to separate psi j into fast decreasing and slow decreasing, I can always move the fast decreasing stuff to the low decreasing stuff, right? And get still a decomposition of slow and fast. So is there a sense in which this particular decomposition is unique?
So this particular decomposition is unique. Once once you have a capstone that is identified, which is in the class of models that we consider, this is unique. Later on, I will introduce another decomposition which is unique of the Beveridge-Nelson type. For the macroeconomists know it like that, even though this is available in other contexts, this decomposition. And that's also unique, but it's different because that identifies the long memory component as a fractional noise. Here it is not the case that it's a pure fractional noise. It could have a contamination from the short-term coefficients, let's say, from the phi coefficient in the Arfima 1D0 case, right? But the uniqueness is there, right? Within this class of decomposition, right? But there are several ways of doing so. This is my point. There are several alternative ways of achieving the decomposition in real time. I will show later on one.
Okay. Thanks.
Welcome. Okay, so just to illustrate, a very simple case arises when there is no short-term component, right? Which is in the fractional noise case. In the fractional noise case, we have that the short-term coefficients are zero, right? And everything is longer. And you recover the formula that we know already from the psi-j coefficient, from the derivation of the infinite moving average polynomial. So in this case, the psi-j would be derived from the Puramadi-Hurwicz formula like this. And then you can show very easily that you can obtain the coefficients using this recursion that eventually leads to the classical formula involving the gamma function there. Okay, so that's for the fractional noise coefficient. And then you have a corollary to the theorem above. You have nice formulae in the case in which White is an Arfima process. If White is an Arfima process, there is a cancellation of the k. So remember the k in the Puramadi-Hurwicz formula. We have a k here. We cancels out in the case the process is Arfima, because there is a k in the denominator also here. And you get this nice formula here. So you get nice recursive formula for computing these coefficients. Now, perhaps there is too much information in this slide. We can see a particular case, which is the Arfima 1D0 process, in which case the short memory component is due to the fact that there is this autoregressive coefficient, which is non-zero. So Puramadi-Hurwicz will give this formula, which can be written down as a recursion. And replacing, so we can decompose psi-j into the long and the short component. And for the long, we have the usual formula. You take the average of the first j component and you multiply it by d. And this is multiplied by phi in the case of the short-term coefficients. And you get this recursion here, where you see now that the phi plays a role here. Instead of having one, you have a phi there. So that's just an application which is relevant for the Arfima case, in which you have only one autoregressive factor. Moving average case, very similar. So I will perhaps not comment on that. So again, you have a decomposition of the psi-j into these two components, usual formula for the long term, and for the short term, you get this. Right, in which now you have a theta here, a coefficient between -1 and 1, multiplying this recursion here. Okay, so how do we use this result? Well, you can provide a decomposition now in this sense. Let's see how we can use this. We have separated the impulse response function of the fractional process into two components. How do we use this? Well, let's go to the decomposition of Yt into what is predictable using the past and what is not predictable, which is the innovation, right? So let's now consider the decomposition of the predictable part. The predictable part can be decomposed into a part that is due to the long and a part that is due to the short memory component. And they take this form. Essentially, this is the effect. So the first one, the long term, arises because of the combination of the past innovations using the psi-L coefficients, right? Or you can use the pi-L coefficient to express this as a function of the past observations of the process. And the short term would be accumulating the xi using the psi-S coefficients, right? So that's how the decomposition arises. So the predictable part is broken into two components. One is due to the effect the predictable effect of past shocks via the long-term coefficients, and this is via the short-term coefficients, right? And this is one decomposition that we consider. Now, the importance of the short-term component would be channeled through this, right? If this is close to zero, so the short-term component matters little for predicting the current value from the past, right? So that's one decomposition. As I said before, there is also an alternative decomposition in which I had done some work before. In economics, it's called the Beveridge-Nelson decomposition, kind of, that arises from integrated process of order one, essentially, but also there are extensions to other order of integrations. But you see, there are also precursors of that, and I put down some references. It's a popular decomposition. Now, this is a decomposition that works in real time now. And it's different from the previous one, but it also offers some insights into the role of the short term as opposed to the long term component. So let us consider a fractional noise process. This can be decomposed into a long term and a short term component, where the long term is a fractional noise process. The fractional noise process is driven by the same innovation as the original process. You see the fractional polynomial here. And the psi1 is the sum of all the psi zeta coefficients of the short memory component, right? And the CT is this component here, driven by shocks zeta t. And you see a polynomial, zeta dagger. Zeta dag is a Lat polynomial, which satisfies this equation, right? So if you have worked with the Beveridge-Nelson decomposition, which arises for the cases when D is exactly 1, you will recognize it. So if D is equal exactly to 1, MT would be a random walk, right? Psi1 would be the persistence of the shocks, meaning the amplification of the shocks or the reduction of the shocks when they are integrated into the level of the series. And CT would be a stationary component, a short memory component, when D is equal to 1. That's the classical Beveridge-Nelson decomposition. Now, it can be extended to any D like this. And now here you would have that what drives CT is an anti-persistent process if D is in the range from 0 to 1, right? And this is would be the impulse response function of the response to this fractional anti-persistent shocks. In terms of the observations, you could obtain MT using this lag polynomial applied to the original observations. And CT would be a function of the differences depending on this polynomial. This is how you can extract these components in real time in terms of the observation. And these are the formulae for the noise, right? So again, this decomposition is available. It's an alternative decomposition that decomposes in real time. Now, the MT component is identified as the fractional noise in the series, right? It's the fractional noise component which you have removed and distilled from the time series. Now, again, you can show that under the original assumption, and assumption 2 in particular, the impulse response function of CT declines to 0 according to this rate, which is the same rate as we saw for the other decomposition. Okay, so how does it work in the Arfima case? This decomposition in the Arfima case is such that MT would be a fractional noise component driven by the shocks multiplied by 1 divided by 1 minus phi. And on the contrary, the short-term component would be, say, an autoregressive process of order 1 driven by fractional noise shocks rather than pure white noise. Sometimes this is called, this noise here is called pink noise, but here it would be anti-persistent. Similar story for the Arfima 0D1. in which case you have a moving average of order 1 short-term component. And again, the MT component would be fractional noise driven by the shocks now, and CT would be this fractional noise process now, multiplied by minus theta. Now, in the classical Beveridge-Nelson case, D is equal to 1, so this would be pure white noise, right? Pure white noise, CT, and this would be a random walk. But here, D can be fractional, right? So this is another celebrated decomposition. It has a slightly different flavor. It exists and it's unique, so this is the result. It has a different flavor from the Beveridge-Nelson type of decomposition that we have in macroeconomics when D is exactly equal to 1, because in that case, the MT is also an indication of the long-run forecast function. So MT tells you what is the value of the process if you were on the long-run path. Here, for a fractional integrated process, the long-run path is mu, essentially. So it does not coincide with MT. So the interpretation is slightly different in this sense. But it's a decomposition. It's a separation of fractional noise from the anti-persistent component. Still, it is like that. Okay, so now let's see what is the importance in inflation and realized volatility of these components. We first consider this time series, which is the monthly US inflation rate for the US. This is the time series that we consider along with the sample autocorrelation function. And what we do is we fit a fractional exponential model to this time series. What is this model? Well, it's the model such that the spectrum is the log spectrum is linear in the coefficient. So this is why this is a nice model. And this is, you can think, is a generalized linear model for the spectral density, because the logarithm of the spectral density is a model that is linear in the underlying coefficients, and the coefficients are the CKs, right, and the D parameter. So it's a generalized linear model for the spectral density of a stochastic process, and it originates from the Fourier series expansion by truncating this expansion at a particular lag, trigonometric lag K, capital Kappa, sorry. Okay. So this is the model that we fit. Now, if we fit it by maximizing the width likelihood, right? There is a nice algorithm that is illustrated, details are given in the appendix. So it's very amenable to computation. So you can fit this very nicely. And we get two solutions depending on the selection of capital K, depending on the Akaike information criterion or the Bayesian information criterion. Here we report the results for the big selection, BIC selection, and these are the estimate of the coefficients. D is estimated to be 0.54, slightly above 0.5 in the non-stationary region. And these are the capsule coefficients. They are all negative. And you see the exponential of C0 of this estimate will give you the prediction error variance of this process. In terms of the spectral density, so this is the log periodogram is plotted in red. This is the log periodogram of the series. And you see the fitted log spectral density, the logarithm of the spectral density that is fitted if you select the model by BIC, a smoother plot. If you select the model according to the AIC, you get more wiggles. So it's a more wiggly log spectral density that is estimated. Now, if you exponentiate the spectral density of the short memory component, so what I do is the following. I take the exponential of this bit here, right? That's the estimate. Once you replace the C with the hat, with the estimated coefficients, that's an estimate of the short memory spectrum. And it's given here, right? It's not very far from white noise, but it has this peak here. And this is the estimated short memory spectral density when you use BIC in solid blue and in dashed blue when you use the AIC. Okay, so what do we make out of this? So what are the implications for the importance of the short memory component? Well, let's go through the first decomposition. The first decomposition, let me recall, is this one, in which we decompose YT into the predictable part due to the long memory, the predictable part to the short memory plus noise, plus the ones that I had prediction error. Okay, so the coefficient, the Psi-J coefficient implied by the model are this. You see these little gaps are due to the short memory component, essentially. These are the autoregressive coefficients, the Pi-J coefficient. The first one is 1, this is Pi1, Pi2, and so on and so forth. They go to 0 in this way. So the decomposition of the two polynomials is such that the psi-L are given here. You see the decline to 0 rather smoothly, right? And as fast as the original ones, I would say. And then you have the short memory components, also in red here, the psi-S. So this component here, they go to 0 like this. And for the autoregressive polynomial, they go like this to 0. Now, when you quantify them, when you compute actually those components, so now we are at the point of computing this and computing that, you get this result. So in orange here, you see the epsilon. So these are the one-step high prediction errors in these dots. The long memory component would be the blue one, and the short memory would be the red one. And you see that the dominating component for the one-step ahead prediction is the blue line. So it tracks the series quite well, and it absorbs most of the variability there. When you consider the decomposition, the second one, which is the Beveridge-Nelson type decomposition, so let's go back to what we are doing here. We are essentially computing these components, right? So we are deriving them from this result. And next we will be plotting MT and CT. This is what you get. So the short memory component will be the red plot, and the long memory will be the blue. Again, you see that this big drop here is mostly due to a persistent move, and then you have also a substantial component. So part of this movement was purely transitory. Part was, due to was more persistent in a sense of this movement. And the conclusion would be that most of the movements here are due to the long memory component. So that's one conclusion that you can draw. And this long memory component has a very irregular appearance. So it's we would call it rough. That's would be leading to the next point. Now, coming to realized volatility, for realized volatility, we consider this time series, right? So that's the logarithm of daily realized variance. It's a daily time series for this time span. When we fit the fractional exponential model, both AIC and the BIC select order k equal to 1, so they converge to the same model, essentially. And these are the estimates. So the D parameter estimate is 0.58. And the prediction error variance implied by the model is 0.36. If you fit an Arfima model now, the autoregressive coefficient is estimated on the negative side, minus 13, sorry. And the D parameter is estimated to be very close to the estimate that we get from the first parameter estimate, 0.57. The prediction error variance is a very, very similar estimate as well. So in terms of the spectral density, so compared to the log periodogram, which is the red plot, you see the log spectral density estimated by the FEXP and the ARFIMA. They are virtually coincident, so you don't see any difference. And when you plot the estimated short memory spectral density, they are virtually identical. So the short memory component has more power in the high frequency, very little in the low frequency here. So in terms of the decomposition, you see on the left the decomposition due to the first, in terms of prediction, the predictable part due to the long memory is plotted in blue, captures most of the variability again. The short memory component is small, is the red plot here. And superimposed, you see the XIT, the one-step height prediction error, right? So that's the first decomposition. When you go to the second, again, the message is that most of the variability is captured by the long-term component, which is the fractional noise in the series. And this component would account for very little, is the short memory component of the Beveridge-Nelson type decomposition. Again, the conclusion is that the permanent component is rather rough. Let's call it like that. It has this rough path. And so the main point here is that the kind of permanent components or the long-term components that we distill from this time series is typically rough. What is the connection with the roughness volatility literature? Well, we could quantify, so a fractional process, even in the positive range of D, where you have long memory or persistent long memory, possibly non-stationary, is typically rough. Meaning that if you look at the changes of this process, they vary a lot, right? So if you take the variation, the changes of this process here, or the realization of this process, they are very rough. And the measure that we propose is the following. Let us consider sort of the variance of the first differences of YT scaled by sigma square. Sigma square is the prediction error variance. So if you assume that the shocks to the process have a unit variance, and then you compute the variance of the differences of the first order differences of the process, you get a measure of roughness. How does it work? Well, if you have a fractional noise process, the variance of the first differences of the scaled, assuming that the shocks have unit variance, would be this function of the D parameter. And this is a measure that decreases as D increases from 0 to 1. So the least rough process would be a random walk. When D moves towards 0, you get a rougher process that is more rough than a random walk. The most rough would be a white noise, in a sense. So this measure of roughness decreases monotonically from 2 to 1 as D increases from 0 to 1. And this will give you a measure of how rough is a fractional noise process, in a sense. Now, also, the short-term component contributes to the roughness. If you have an ARFIMA process with a -5, that will contribute to the high frequency of the process, and that contributes to the roughness of the process because it oscillates more. The variance of the first differences is larger again if you set the variance of the shocks to unity, the size of the shock to unity. So for more general processes, what we propose is the scaled variance of the changes of YT. So this is a measure of roughness that we consider, which we think is compatible to the idea of roughness that they have in rough volatility literature. So what is the logic of this measure? Now, take this middle formula here. What you see, if W omega were equal to 1, you would see the variance of a scale version of the variance of the process. Here we have the variance of the differences of the process, but think of the spectral density f of omega, scaled by sigma squared. This is a scaling factor. Now you multiply this by this factor, W of omega. W of omega is the is this factor here, right? It's twice 1 minus cosine of omega. So it's the square gain of the first difference in operator, nothing more than that. Now, the reason why you multiply the spectral density by this factor is that now you make a contrast between the high frequency, so this would be high at the high frequency, and the low frequency. This factor is close to 0 at the low frequency. So this tells you how rough is the process, in the sense, what is the role of the high frequency component in the process, in a sense, right? So that's the measure that we propose. And so this will be affected also by the short memory component, because this will contribute to the roughness by this factor here in the third line. Just for the sake of illustration, let us consider how this measure of roughness behaves for an Arfima 1D0 process, which is this left plot here. Now, this is a function of D, the memory parameter, now here in the range from minus 0.4 to 1, and it's a function also of phi, the autoregressive coefficient. And the maximum roughness, you have it for D small, possibly negative, and phi going to minus 1. As phi increases, the roughness decreases, right? The roughness decreases because there will be more component at the 0 frequency and less at the high frequency, and so on and so forth. For a fractional noise process, this is the story. Phi is equal to 0, and the roughness decreases as D increases, right? So that's the story. So this is showing how the short-term component could contribute to the roughness of the process as well. So this is the measure the behavior for the Arfima 1D0. This is the behavior for the Arfima 0D1. Now this is a function of the theta parameter, which is the moving average parameter, right? So if you have a theta going towards 1, you have more roughness, and less so if theta goes towards minus 1, in which case you have something that has a low frequency component, which is higher in general. So that's pretty much it, and that's the end point of the presentation, essentially. These are the references that I quoted, and that's pretty much it. So thank you very much for your attention.
Thank you very much, Tommaso. Then I'm stopping.